Okay, yes, fundamental theory of calculus, part 2, we covered everything. We know that it helps us to evaluate definite integrals just by knowing an antiderivative for the integral. We also started working on fundamental theory of calculus, FTC1, which this time talks a little bit. This is the topic of the first one seems a bit different format, but at the end I will mention how these two are related. They're saying basically both of them are saying different sides of a same coin, and we will discuss that. But I remember that last time we left, we weren't able to complete the examples I wanted to complete, so I will start reminding you what was the fundamental theorem of calculus part 1, do some examples and cover the remaining parts that we are supposed to cover. Okay, so first is recall that fundamental theorem of calculus part 1 says how we can handle functions defined like this. The functions who are defined by definite integral, this way, are good functions. They are differentiable. And the derivative, the theorem of calculus part 1 says, is nothing but the integral. And then we worked on some examples. For example, we saw that, okay, if I have 0 to x of, say, cosine of t squared dt, well, evaluating this integral is not easy. Fundamental theorem of calculus, the trick there says that you don't need to evaluate this integral. Any function defined this form, the derivative is just given by the integral over there. Yes. And then, well, we saw also an example like this one, that d dx, you go from x to 1 of, say, t2 over t3 plus 3 t plus 1. Hopefully it's a good function. I'm just trying to get that one done. And we notice that this such function is not covered right away through this. The reason that's not covered right away is that, well, here the x variable should be the upper limit. And, well, you can do that. You can play the same game after you apply the property of integral, flip this thing up there, and you know that when you're flipping bounds up an integral, you pick a negative sign. So in that case, there will be negative, and then the rest goes as we have. So x squared over x cubed plus 3x plus 1. Now, what about the function like, let me see if I can keep this for 0x squared sine of t squared plus 3t dt. Well, I'm not interested in the function itself. I'm interested in deriving that. Okay? In deriving that, finding the derivative of that. This one, I'll give you maybe 30 seconds. Talk to your friend. You want to see what is different about this function now, and how we can approach in some mathematical way. If you're not using the right a theorem name, you're missing a point there. Okay? 30 seconds, you're discussing with your friend how is this related to FTC 1 and how you can handle that. Go ahead, 30 seconds, I want to hear chatting there. Go ahead. That's t squared. Okay, I want to hear what is the main difference and how I can handle even one of those points I will take here. Yes, please. Upper bound, unlike the original version of FTC, is not X. Oops, I am so sorry. Are you okay? Okay. You will become the doctor. You can fix this. Sorry about that. So, upper limit is not X. It is a function of X. And in that case, we can split this into two cases. If it was just 0 to x of sine t squared plus or minus or plus 3t dt, then I know how to integrate that, yes? Because this is FTC1. But what I am dealing here is d dx of that function, but instead of x, I plug in x squared. What is the rule to differentiate such function? What is the rule to differentiate such function? I want to hear that. Yes. Chain rule. You have, instead of x, you have a function there. So you get derivative of x squared times g prime, but you have to plug in x squared. How is that going to help? Because g is just a simple thing, and we know what is g prime. It is sine of x squared plus 3x. Done. Yes? Instead of x, I have to plug in x squared. So I get 2x sine of x to the power 2 to the power 2 fourth plus 3x squared. The game is on. The game is the same thing. FTC here, you have to combine it with the chain rule. And if I want to write it in one form, sometimes I like it, sometimes I don't like, but anyhow, calculationally, you have to do this operation. I hope that by that example, you have now seen what's going on. If instead of x up there, I get a function, let's call hx there. FTC1 plus chain rule tells me that this is not f at x. It says it is f at h at x, but you have to multiply this by h prime. So you have to multiply it by h prime. That way you will be able to do that. Yes, please.
I think you did it for x squared, but I said x cubed.
Sorry, what was that?
At the really top of the board, there should not be 3x squared, it's not x is how it says. Then equals 0 to x cubed.
See, g prime x is this. I'm plugging in x squared for x's. So this will be x squared to the power 2x4, 3x squared. Am I missing maybe something there? And the derivative of x squared is 2x.
I thought we were doing it for x cubed.
This is x squared. Oh, maybe, okay. Do you see it as x cubed there?
Yeah, my bad.
I'm sorry, no, that's actually, there was a line from previous writing there. Is that was, okay, good. Yes, thank you. So h prime times f at hx is how you will deal with that, and that's the story behind it. How about you do handle these ones, d dx of 2e to the power d dy, x to the power y dx. Okay, let's go on. Let's do these two examples. I'll give you 90 seconds. I'm expecting you to be able to finish that example, but I am hoping that you will be just doing few steps from this before that 90-second ends. Go ahead, please. Do that one, and then we go through. Thirty seconds left. Well, I have to repeat this, reminding you that always in questions like this, you're dealing with two different variables. The variable inside the integral, the integration variable, that's just a disappearing variable that we have just to fill a spot there. Whenever there's an integral, there must be a variable. In this case, it happened to be x. The important variable for us is the one that we are differentiating with respect to. And we will see functions of that variable appearing there. So at the end, we will have a function in terms of this one. Now, I have upper limit is a function e to the power y. We have to differentiate that. And then we have to plug in e to the power y for each x I see there. Here, differentiation is with respect to y. So I get e to the power y times e to the power y times e to the power yx. So that is another way of writing it, yes? Well, you can still go one more step and say that, oh, this is nothing but Because they have the same base, we can simplify it, right? Any questions, any comments there? The last few steps are simplification. The key point is that the first one after I wrote down, after the integral. How about this one? How should I start this? Or what is different about this one when I compare to the other ones? If I can hear about the difference, that would make me happy. Yes, please. Both bounds are functions of x rather than, well, so far we had one of them. Originally we had only x in the upper one. Okay. How to handle this one? How to handle this one? Anyone? Yes, please. We use the properties of definite integral when it comes to the boundaries. Meaning that I can rewrite this integral as sine x to any number you choose. I'll write 0. Plus from 0 to cosine x. Now I have to put everything in. That was what my integral, the original integral, can be written in. Now I have to differentiate these two functions. Why did you apply that step? Because I want to have integrals that have one of their bounds as constant. Now I have, instead of two integral limits being functions, I have two integrals. Each one has only one function, upper or lower integral limit. But I can fix this one by bringing it up, swapping that thing up there. Wait, you're not allowed to change the bounds unless you multiply the whole thing by a negative sign. And for this one, okay, it is already upper bound, so I can keep it that way. Now, I'm back to that FTC plus chain. FTC 1 and chain rule now tells me that I can plug everything here, pi the derivative of this, cosine x, e to the power minus sine squared x. Well, there was a negative sign. I have to keep that negative sign still there. Plus derivative of this guy, which is minus sine x, times e to the power minus cosine x. Okay. If both of the functions, or both of the limits, are functions in x, with respect to which you're differentiating, then you can put these things all in one form. Again, I don't need more than FTC and some properties of integral. That's all I'm using. But just to simplify things, if I have two functions here, gx, hx, and f at t dt, this derivative is going to be differentiate the upper one times f at hx minus, where does that minus come from? Because I will flip this thing up and I'll get g prime f at gx. that will cover all the cases that can come up when it comes to FTC. Differentiating functions defined by definite integral while we're playing with the limits of integration. Any questions, any comments? Today being Friday means that we will have a iClicker question. And I'm going to open the iClicker question if I don't receive any question. Can someone confirm that you can see the question now? Yes? Okay. Go ahead, please. You have 90 seconds to do that one. Okay, so here, well, this is the most general version that you can find. It has all the properties, chain rule already implemented in it, and we will need here. The only thing you need to make sure that you understand, x is the integration variable, and t is our actual variable. So at the end, everything should be written in terms of t. And the way it works, derivative of upper limit times plug in upper limit into your integral. 3t to the power 4 minus 2 times 3t to the power 3 minus 3t minus 1. That is only half of the story. The other half comes from the lower limit, which is minus derivative of lower function 2t times plugging the lower function itself into your integral. T to the power 8 minus 2 t to the power 6 minus t squared minus 1. And there we go. Well, I think there's a simplification there. This is 81 t4. This is minus 54 t cubed, and the rest is like that. And that gives us the answer is it D? I think so, yeah. Any questions, any comments? Okay, I'm going to close iClicker in 5 seconds. If you haven't done it, please, quickly. 10 seconds, okay. Okay. I think we're good now. That is all I wanted to say about fundamental theorem of calculus. There are different applications you may see in different places, but now you have two strong tools, which basically they're saying the same thing, that one to evaluate the integral, the other one is definite integral, the other one is to differentiate functions defined by definite integral. But now we want to do more. We want to evaluate, find more tools and techniques to evaluate definite integrals, or in general, finding the more general antiderivatives. One of the techniques, the only one that we will cover in this course, is called substitution. For, well, here is indefinite integral, but we will cover the definite integrals later. Let's start with a simple example. Very simple example. Recall that by indefinite integral, we mean just find antiderivatives. And how do we find antiderivative of x plus 3? Yeah. Yes, please. We use the properties of integral, expanded, and then power rule, which says antiderivative of x to the power n is 1 over n plus 1 x to the power n plus 1. Okay? What will happen if I do have 2 there? How do you find antiderivative of this function? 10 seconds. 10 seconds. Talk to the friend. I need to hear some answers. How do you find that? Yes. How do you find it? Do you want to tell me? Chain rule. Oh. Oh, chain rule. Ouch. Chain rule is good, but chain rule is for differentiation, not anti-differentiation. Actually, what we are covering is basically going to show that. But let us see. Who else was trying? How do you do that? Yes, please. You guys all know more than I do, but there's a simple way to deal with this. Let me see. Yes. Expand it, yes? It's to the power 2 expanded, and then you deal with that. But you want to expand it still? Do you want to expand it still? Well, questions like this should remind you of what your friends already mentioned. In the case of derivatives, when I have derivative of x to the power 24, I know how to deal with that. And then, if I have a function of gx to the power 22, then we do what is called chain rule, yes? Then the chain rule, we do exactly same steps that we have done here. 24, gx to the power 1 less But we have to multiply there a g prime x. Yes? We have to multiply there some g prime. Now, I want to reverse this process. When you want to reverse this process, the way you have to think is this. I can turn this differentiation or anti-differentiation into this one. By simply knowing that, if I have the derivative of function multiplied there, I can turn this whole thing to that. I can differentiate x to the power 20, 24, and then everything else will go like that. What I mean is this. Differentiating these things, I'll get back to that example, but in general, if I have a function of gx, finding antiderivative of such function is not easy. Unless you have a factor that you receive in the chain rule. In other words, if you have g prime of x multiplied to your function. In that case, we can turn our integral into a simpler integral by swapping or changing the variables. This is called substitution. How do we change it? We set u to be our gx. Okay? And I'm going to rewrite our integral. But I'm choosing a new variable, meaning that my integral, at the end, everything here will be in terms of u, not x. And I already see that instead of f of gx, I will be able to put f at u. Okay? How about dx? I am now allowed to replace dx by du. That is a no-no. If you change your variable using this recipe, you're setting your new variable u to be gx. The du part of your integral is going to change this way. dx is not du. G prime of x times dx is du. So I can deal with this part, that's f at u, and this whole thing here is going to give me du. What did happen? I changed a thing like this to a thing like that. But you didn't evaluate your integral. Substitution doesn't claim that I can evaluate your integral. Substitution says that I can change your integral into another integral. If you have chosen right substitution, and if the integral is nice enough, hopefully this new integral is going to be a simpler integral compared to the one that you had originally. And then evaluating this integral is a different story. Let's see this in the example that we have up there and see how this is going to help us with evaluating that integral. Your friends already pointed out that, okay, I have x plus 3, 20, 24 dx. I can change this to u to the power something. Okay. I can take that to be my function u. And that will give me u to the power 20, 24. How about du? Well, du is not necessarily equal to dx. You have to take derivative of that, which in this case is 1 times dx. Oh, in this example, du and dx are the same thing. In other words, I can take dx and replace it by du. Wait a minute, before it was x plus 3 to the power 2024. Now it's u to the power 2024. Where did you simplify that? I did simplify a lot if you carefully look at it and try to evaluate it. Because now, here, I only need to use the chain rule. U to the power rule for integrals. Integral, now we are integrating with respect to u, and this is u to the power some number n. So the integral would be u to the power m plus 1 divided by m plus 1. Nothing more. I don't care what was inside that thing now, yes? And it seems that we got rid of integral. But if someone gave us this question, left the room, comes back, and says, what was the answer? I give him or them this value, this function. Wouldn't they ask, what is u? What the heck is u? My integral was in x. You're giving me something in u? What is u? And they are right, because u is something that we introduced. It's a temporary variable that now we have to get rid of it and turn everything back into our original function or original variable. In our case, the original variable was in terms of x, and I know that I just need to replace u by this last step is as important as all the other steps that you do there. Yeah? Any questions, any comments here? We are trying to find integrals of this form, changing variable. What u would be proper variable. There is one hint always there that you have to be able to find the derivative of that gx as a factor of your integral. But in general, you need to do a lot of practices. That's the story now. Let me write a few more examples here. Go ahead, please. I'll give you 90 seconds. For me, the important steps for you to do is what is the proper u, then how do you replace your x integral by u integral. I don't want you to continue after this step. I just want you to perform the substitution. Go ahead, please. 90 seconds. And yes, you're welcome to talk to the friend sitting next to you. The important part for doing substitution or choosing the right substitution is looking for this derivative. Whatever you're taking, it should have the derivatives as factor of the integral. In this case, what would be the right u to start with, maybe? Yes, please? The function, the whole function under the square root. If I take u equal to that, wait, how should I make sure that this is a good choice? Here is the fact that du is supposed to be 3x squared dx. And 3x squared, the derivative of that function, is the factor of the integral. In other words, when I'm performing u substitution, 3x squared dx will be replaced by du, and square root of 1 plus x cubed is going to be nothing but square root of u. Square root of u, because 1 plus x cubed is u, and du is 3x squared times dx, and I have it there. Well, what will happen from this point on? This is again u to the power half. Remember, this is power rule, so I will have 1 over half plus 1, u to the power half plus 1 plus c, or plug it back, 1 plus x cubed. That is what we have there. Okay, what about this other one? What is the good choice for you? Yes? Tan x, yes? Tan x, but what is the sign you see there? Because the derivative of tan x, which is secant squared, is the factor of your function, your integral. So u equal to tan x looks promising substitution, and then du is going to be secant squared x dx. Well, this is e to the power u, because u is set it to be tan x, and dx times secant squared x, or secant squared x times dx, is nothing but du. And that's a good sign for me, because now that complicated integral changed to a simple integral in u, just e to the power u, and I don't need anything but one item from the antiderivative table, antiderivative of e to the power u with respect to u is e to the power u. But I'm not done until I put back in the x function that we started with. Okay. How about this one? What is the right, or what is the first candidate to do 1 over the u? Yes, please.
3x plus 1.
3x plus 1. Let's see. U is 3x plus 1. Then du will be 3 dx. Wait, where is 3? Yes, please.
Your d would be like du times 1 over 3.
Either that way, or let's look at this a bit carefully. The coefficient that I'm missing is a constant. Constant, I can always play with constant, because constant can come into integral and leave integral without changing it. In other words, I can multiply my integral or integrand by 3 and divide the whole integral by 1 over 3. That 1 over 3 can come in, cancel 3, and we are back to the original function. Yes? But by doing that, now I have 3 dx is equal to du, and I have u to the power 10. Okay, I picked that factor of 1 over 3. I should bring in that factor of 1 over 3 as well. Okay? If the only missing part from your derivative is that constant term, constant multiple, you can fix it this way. It's not very important. You just always multiply, divide outside, and that will give you what you're looking for. So this will be u to the power 10. The antiderivative is u to the power 11 over 11. There is a 3 there, so I'll get that one. And then you have 3x plus 1 to the power 11 over 33. Don't forget that plus c, which is important. Yes, please.
Can you explain why you couldn't have just made u equal to x?
I didn't say you cannot do that. I will suggest that later on. Wait, maybe I missed your question. You said that we can set u to be...
Well, you said it's u equals 3x plus 1. Why not just go u equals x?
Oh! When you fix u, you don't have any choice here. You just say du is derivative of that, which is 3 times dx. You don't have any choice. After you fix u, your du is given by your original function u. Well, we need to do so many more examples. On Monday, you come back, I'll start with this, and then we will move to the substitution for definite integrals, which has a little bit more story. Have a great day, good weekend, and see you all on Monday.